Hello everyone, I am Pragya Srivastava. I am here to record a lecture on control system. The course code is KEC 602. Presently, we are discussing its unit 2, which is state space variable model. Previously, in this subject, we have done unit 1, where we were studying introduction to control system, and also we have studied transfer function analysis. Now, transfer function analysis, we will be studying how a transfer function analysis and state space analysis are different in terms of assumptions and concepts. So, first thing which we will be discussing is why state space model, introduction to state space model, examples of state space model, and then what is the terminologies to implement a state space model. So, all these things we will be covering in my lectures. Now, we have to study what are the benefits of transfer function and what are the limitations of transfer function analysis. Of course, there are two kinds of analysis. One is transfer function analysis and other is state space analysis. Now, previously when we were studying the introduction and we were studying transfer function analysis, we assumed that initial conditions are 0. So we have also discussed this initial condition 0 with help of some example. Let's say we have to move from point A to point B, and point A and point B are 100 kilometers apart. So, the work to be done is for 100 kilometers. Now, let us assume that instead of being at point A, we are at point C. So, the distance between point A and C is 20 kilometers. So, now ultimately, I have to reach to point B from point C instead of point A. So, initially, I have covered a distance of 20 kilometers. So, the net distance which I now need to cover is only 80. So, I have to make my calculations and I have to make my analysis only for 80 kilometers, not for 100 kilometers. So, let us start analyzing this model with the help of transfer function analysis. Now, transfer function analysis would say that initial conditions are 0. It means transfer function analysis will assume that I am not at C, I am at A only. So, this benefit of 20 kilometers I will not get. So, just because I have made an assumption that initial conditions are 0, I am landing up in an incorrect estimation of my model. So, this is a drawback, this is a limitation of transfer function analysis. Whereas, in state space analysis, we include the initial conditions as well. Now, let us start with the benefits and limitations of transfer function analysis point by point. Transfer functions are defined in Laplace domain and are generalization of Fourier transform. So, this makes the calculations and the derivations easier. We do it in Laplace domain. Can be used only for linear systems. It can be extended for some non-linear systems also, but only some. Okay. So, the thing is, it can be used only for linear systems. Input-output view. The system is input-output view. Input can be signals of various frequencies, bandwidth of control systems, and limited to single input, single output systems can handle MIMO systems with complexity. So, here we can have multiple input, multiple output systems, but again it comes with the impact of complexity. Very dominant in the industry. Presently in the industry, we are using the transfer function analysis with a huge range of application, The internal behavior of the system is not known. So, this is also a drawback or limitation of transfer function analysis. Next is, the first line itself tells us about the example which we have just studied with the start of this lecture, like we are at point C instead of point A, and we have to move to point B. So since we are not assuming that we have already covered 20 kilometers, so we will make an incorrect or wrong estimation of transfer function or the model. Transfer function is only defined under zero initial condition. So we have to assume that the initial conditions are 0. The relationship between the coupled system is not explained well. Now, internal behavior of a system is not known. That is, what is happening within the system is completely unknown to us. So this is what we can categorize. This is something which we can categorize as limitations or demerits. So volume, we can see that it is a chemical process plant, and here we have volume of steam, input temperature and compressor pressure. So these are number of inputs. Okay, these are the number of inputs to the systems. So some processing is taking place inside the plant. Now here we can call it different subsystems. Can be isolated and examine controllability and observability. Measured pressure, so these are the outputs. Measured pressure, measured volume and measured temperature. So these are nothing but the outputs. Coming on to more and descriptive study of state space model. Now, mathematical model that connects input, outputs and internal variables of the system, like which we were not knowing in case of state space analysis. Transfer function analysis. We were not knowing what all is happening within the system. We were not knowing what all variables are used within the systems. We were not knowing what are the states, which are the intermediate states in carrying information from input to output. So these variables, these substates, subsystems, intermediate variables, all these things were never known to us when we were studying transfer function analysis. Now, mathematical model that connect input, output and internal variable of the system are related by first order differential equation. So we will study that the three of them are related to each other. State space method of design came into existence during 1960s. So this is not a new process. This is not altogether a non-tested process. This is verified and this has come into existence in 1960s. So we have enough of studies, we have enough of discoveries already done on state space model. This domain of design referred to as modern control design, when the basic law of physics applied to the system, then we get a set of differential equation. Now, what they're trying to say? Let's say we are talking about some displacement which is taking place in a block of mass m when we are putting some force on it. So let's say there is a mass m and we are applying some force F, and with the help of by the virtue of this force, there is a small displacement which is delta x or dx in this position, and accordingly we have certain acceleration. Acceleration can be written as d2x by dt square, and here also we can have certain other parameters. This is acceleration, and then we can have velocity dx by dt. So this is nothing but velocity. So what we are telling, these are the basic law. What have I done? I have applied just some basic physics law on mass m, like applying force on mass m will result into some displacement dx, and as a result of this displacement, as a result of some velocity, there will be some acceleration, there will be some displacement. So when we apply this physics, when we apply this basic understanding of laws of physics, we get some equations. So of course, like we have F is equals to ma. This is also equation, right? So of course we will get some differential equation for any physical system. So these differential equation shows the dynamics of the system. We can see that how the dynamics means how the movement, how the displacement within the mass m can be studied. State space system refers the past, present and future conditions of the system. So it is including the past condition, it is including the previous condition, the present condition, the future condition. So it is completing the 360-degree physics. So we can say that it is more accurate than the transfer function analysis, wherein we were not considering the initial condition. So this is what a state space model is. Coming on to the representation. State space model is a representation of dynamics of a system in the form of set of n first order differential equation. Now we will study more and we will understand this statements more when we will be solving some example. So instead of having just one differential equation, we might have n differential equations. We can have 3 differential equations depending upon how many elements we have and how complex the system is. We can have n number of differential equations. It converts the nth order differential equation which governs the dynamics into n first order differential equations. So we have let's say we have second order differential equation or we have third order differential equation, and then these dynamics will have 3 first order differential equations or 2 first order differential equations. So number of states, how many states do we have, will be order of differential equation. For example, an electrical system is usually equal to number of energy storing elements. So what are the energy storing elements? Electrical system, what all elements we can have in an electrical system? Let's say we have a capacitor, let's say we have an inductor, let's say we have a resistor. So depends which one, how many energy storing elements are there. Depending upon the number of energy storing element, we will have that will signify the order of differential equation. So I'll repeat again, these things will be clearer and clearer once we see example on this. Now here we are. So this is a electrical element, electrical circuit and electrical network, I can rather say. And for that electrical network, we are going to categorize the variables using state variable analysis. Now, what is happening? We can see that there is an input voltage and we are studying this in time domain, and of course this input voltage will result into some current which is I of t, and then we have this resistor R, we have this capacitor C. So across this resistor we have a voltage V of R, across this resistor we have VR, across this capacitor we have VC, and then we have, in terms of inputs, we have voltage, or we can sometimes call input variable, and then at the place of output we can have outputs at output as voltage drop for resistor, for capacitor, for inductor. So we can have y1t, y2 of t, y3 of t. So here we can study Vt and It are variables characterized the system for this simple electrical network. They are called as characterizing variables. How can they characterize the system? How they can characterize this network? Depending upon the voltage, we will have the current. Depending upon what amount of current is flowing across the circuit, there will be the corresponding amount of drop. So they are actually, what are they doing? They are characterizing, they are driving the network, they are driving this electrical network. So the output is dependent upon these characterizing variables. So characterizing variables is nothing but input like V of t, I of t. Any output information, of course the output is dependent upon V of t. The output information can be obtained in terms of these characterizing variables. So we can very well understand. Let's say we are just introducing a very small amount of voltage. That small amount of voltage will result into a small amount of current, and the small amount of current flowing through the electrical network will result into a small amount of drop across the resistor and capacitor. So it is characterizing. On the other side, when we increase the voltage to some considerable amount, there will be a result of some considerable amount of current. Accordingly, we will have considerable amount of drop at resistor and capacitor. So what this input or characterizing variables are doing, they are driving their output information. Next is energy state can be characterized by using this variable. Now, if V0 and I0 is known for t equals to 0 and Vt for any particular time instant, external supply and IT is known for t is greater than 0, then we get total information about the system at any point of time. So we can get the complete information when we know the initial condition and we know the values for t greater than 0. So we are completing the entire 360-degree span of this circuit. Like before when the time triggers like t greater than 0, you should know. T equals to 0, you should also know. Now, so one more thing I want to tell you that this this voltage across the inductor here, it is we can characterize it as L di by dt. So we study for this network. Let me draw the network here. This is the inductor, then we were having a resistor, then we were having a capacitor. Okay, so this is VC, this is VR, and this is VL. Now, VL is nothing but L di by dt. That's what we have written here. Okay, L di by dt. And then we have V equals to IR. And then let's see the voltage across. Presently, we are just assuming that the voltage across this capacitor is just VC. So, of course, this VC can be written as integral IT dt 1 by C. Like we can also write it as 1 by C integral IT dt. So presently, for instance, we are just assuming it at VC. Next, so this is the first characterizing variable. The second characterizing variable is IT. So this IT can be written in terms of VC, that is C dVC by dt. These two equations show the mathematical model of the system. Now, we can rewrite this equation in terms of characterizing variables being on the right hand side. Characterizing, let's assume that we are putting all the characterizing variables on the right hand side. So let us encircle the characterizing variables. So where are the characterizing variables? this is the characterizing variable. This is the characterizing variable. Let's put this on RHS. Okay, and rearrange the equation. Sorry. And we are going to rearrange the equation. So this is rearranging the characterizing variable. Here also the characterizing variable is this. We are rearranging it. We rearrange it in terms to get the equation like the differential, like dVc by dt is in terms of characterizing variable it by c. Then we have di by dt. So di by dt is, from the first equation we can see that we can have the value of di by dt, this one. We can write it as, we can divide the complete equation by L. So we have minus R by L it minus Vc by L plus Vi t of t. Now let us assume some state variables, some intermediate variables. So those state variables are x1 will be equal to Vc, x2 will be equal to I of t, and u is equals to Vi of t. Then what we are doing presently, we are just making some substitutions. So at the place wherever we have Vc, we are just substituting it like x1. So dx1 by dt is equals to x2 by c. Again, dx2 by dt will be equal to R by L x2 plus x1 by L plus u by L. Now we have to study that how the corresponding equations have been transformed into matrix. So we will start the complete mathematical model with the help of all the physics behind this in my next lecture. So in my present lecture, we have studied how an electrical network can give us equations which can be further converted into matrix. So we'll be studying the next thing in my next lecture. Thank you.